I'm going to number them now. So let's begin talking about inverse functions for this last part of chapter 2. I'm going to give you a generic old function, and it's going to be 2x plus 3. So we're going to call this f of x, okay? And for this function, let's come up with a couple of inputs and outputs for this. So if I asked you what's f of 1? If I asked you to come up with f of 1, you'd get 5, yeah, right? Because you'd have 2 times 1 plus a 3, and that would give us 5. So the point that would go with this, so the input would be 1, the output would be 5. So 1, 5 is on the graph of the line function fx equals 2x plus 3. Let's do 2 more. What about f of 2? What would that be? 7. That'd be 2 times 2 plus a 3. That'd give us 7. So the input would be 2, the output would be 7. And then let's do an easy one. Let's do 0. What would that give us? Yeah, 2 times 0 plus a 3, which of course gives us 3. So I have an input of 0, I have an output of 3. Okay? Yeah, you feeling good? You feeling good so far? What's the domain of what I have so far? Just the points that I've given you. What's the domain? Well, the domain for this line is all real numbers. That's true. But just in the terms of the points that I gave you, what would the domain be? 1, 2, and 0. What would the range be?
5, 7, and 3.
It would be 5, 7, and 3. Now, of course, the domain is all real numbers for this line. But in terms of the inputs here, inputs and the outputs, just we're talking about domain is 0, 1, and 2, and the range is 5, 7, and 3. Okay, good. So this is pretty much just basic stuff for functions. We have inputs and outputs. We can evaluate functions, and life is going pretty well for us, all right? So let's take a critical look here at what did we do to get these numbers. So the first thing I did was I took a number, any old number x. The second thing that we did was we multiplied it by 2. You guys agree with that? If we're just taking a look at what we did, we multiplied it by 2. And then the third thing that we did was we added 3. You guys agree with that? Okay, so this is kind of the order that we did things, 1, 2, 3. And if I'm trying to understand what an inverse function is, well, an inverse function should basically undo everything that we just did. So if I put a 1 into my function and I get a 5 out of my function, then when I put a 5 into my inverse function, I should get a 1 back out, okay? So if this is the order that I did things, let's try and reverse this order and think about this mentally. So I'll take any old number x, and instead of adding 3, so I'm going to go in the reverse direction, I should do what to my thing? I should do what to my, oh, wait, hold on a second. What's the inverse of adding 3? I should divide. If I put this first, and then this second, and then finally this third, which I'll just call g of x for right now. So that says take x, subtract 3, and then divide by 2. Okay? So that's how I've created this function over here. Now, do these functions look different? Those ones that I've highlighted in the boxes there? They look different, right? But there's something that's special about these, okay? And let's explore this a little bit right now. So check this out. What would g of 5 be? Well, let's see here. That would be 5 minus 3, all divided by 2, which is 2 over 2, which is 1. So that means that the point that I get here is 5, 1. You agree with that? Yeah. Okay. What would g of 7 be? It would be 7 minus 3, all divided by 2, which is 4 over 2, which is 2. So I have 7, 2. And what would g of 3 be? Well, that'd be 3 minus 3 over 2. That's 0 over who cares? Because that's 0. So that means we're going to have the point 3, 0. All right, great. So what is my domain for g of x now? 5, whoops, don't need to underline it. 5, 7, and 3. What's my range for g of x? 1, 2, and 0. Does anybody notice anything about this? X has a very special name, okay? So you should have noticed there that the domain of f of x is the range of g of x, and the range of f of x is the domain of g of x. So, you guys, we call g of x, which is equal to this x minus 3 over 2, we give this a very special name, and it's called f inverse of x. Okay? And the way that we say that is f inverse of x. All right? So we're going to learn how to find f inverse of x. So let me give you any old function here. All right? Let's start off with the function f of x is equal to 5 over x and then plus 3. All right? First of all, let's figure out what is the domain of this function and what is the range of this function f of x. So we're going to use our calculator. So go ahead, take your calculator and open it up. And we want to graph the function y equals 5 over x minus 3. And it should be punched. We have a correction. So 5 over x plus. Okay. So you should see this. You should see this. And of course, it is the inverse function, which we call the Hurley graph. It's the inverse function, but it's been multiplied by a factor of a fifth, which is, and then vertically transposed 3 units up. Okay. So this is what we're looking at here, right? And if you look at mine, I've got one over here for you as well. So it was y equals, it was 5 over x and then plus 3, yes? Okay, good. Oops, what's going on here? Yeah, there we go. So, here we go. Here's our graph. This is what it looks like here. And what would you say? I want to know the domain and the range for this one. So I'll be able to zoom in a little bit more so we can see. Okay, let's figure out the domain and the range for this function. So the domain looks like everything except for what? 0. Yeah, it can't be 0, right? Oh, the wrong way. Can't be 0. And what about the range? Is there a number? Is there a y value that? Yeah, it's 3. Very good. It has something to do with this over here, right? Right about here. Doesn't exist. That would be 3. Okay, good. So for us, we're going to go ahead and put that in. So our domain was all real numbers x such that x was not equal to 0. And that's set notation, and we can see that right there because we're not allowed to plug a 0 in for x. And then we found the range was all real numbers y such that y could not equal 3. And that makes a whole lot of sense because we're moving the graph up 3 units. Okay? So we know everything about this particular function so far. So as long as we define our domain and range here, we can talk about the inverse. So how do we go about finding the inverse? Well, the first thing that we're going to do is we're going to let f of x become y. Y equals 5 over x and then plus 3. That's the first thing we're going to do. And then you may recall that back here in this one, what ended up happening? The domain, which is the x values, became the ranges, which were the y values, and vice versa. So what we're going to do then is we're going to simply switch 5 over y plus 3. So we're going to switch x and y. So step 1, we're going to let f of x become y. Step 2, we're going to switch x and y because when we then apply step 3, we end up algebraically solving for the inverse function. That's why we switch these things. So if I want to solve this for y, I'd say, well, x minus 3 is equal to 5 divided by y. All right? Now, if x minus 3 equals 5 over y, what does y equal? Yeah, very good, right? So that means that y is equal to 5 over x minus 3. And then finally, on step 3, once you've solved for y, you've found your inverse function. F inverse of x is equal to 5 divided by x minus 3. So now we have this inverse function here. F inverse of x equals 5 over x minus 3. So what I would like you to do now is I'd like you to graph the inverse function alongside your regular function, and we're going to take a look at that. And I'll do the same thing here. Oops, I'm in the wrong mode. Okay, if you graph 5 over x minus 3 on your calculators, and then you put it onto the graph, you should see something that looks like this. And we will clear this out. All right. Is that what you guys see? Something that looks like that, right? If we do it on our calculator as well, if I plug it into mine, and I go to y equals, and I do 5 divided by the quantity of x minus 3, and then hit graph. There it is right there. Now yours might have that vertical line in there. That's just the nature of the calculator. That's your vertical asymptote. But if we look at this particular graph, it's the same one, and it's a little bit more interesting, or it's a little bit more clear, I should say. It's pretty much the same graph. Okay, does anybody notice anything sort of interesting that's going on here? Amy, what do you notice?
If like you put a line over there that connects the two intersecting points.
Oh, I see. So if I put a point there and I put a point there and I draw a line that connects them, what is that line? No. What's the equation of that line? It's the identity equation, right? It's the line y equals x. Very good. So if I put y equals x on here, Amy notices that these two graphs are just the reflection over the line y equals x. And that's not a coincidence. In fact, that happens for every single graph and its inverse, which we're going to get into more on Friday. But did anybody notice anything else interesting here? No? Okay, well, let's point out. Let me zoom this in just a little bit, okay? Can you guys give me one point that's guaranteed to be on the red graph? Can you find a point that's easy to identify?
Negative 5, 2.
Negative 5, 2. We all agree that the point negative 5, comma 2 is on the graph? Yeah? Well, then on the inverse graph, what point is guaranteed to be on the inverse graph?
5, 2.
5, no, 5, comma, no, not 5. Don't we just switch these two? Remember we switched the domain and the range? Yeah, so 2, comma, negative 5. And check it out. When I move my graph down there, which you can see. Check it out. There's the point 2, comma, negative 5. So there's the point 2, comma, negative 5. Does that work with every single point? Yes, it does. It works with every single point. So 2 takeaways here. When you're graphing functions and its inverse functions, there will be a reflection over the line y equals x, which we have here. And for every point that is on the function itself, namely negative 5, comma 2, then if I reverse x and y, then the point 2, comma, negative 5 will also have to be on the graph itself. You'll be doing that later on today as well. All right? So here we go. I want you guys to try one right now. Okay? So a little you try right here. Same kind of box. I'm going to give you this one. F of x is equal to 3 over x minus 1. Okay? Please find f inverse of x. What is... Okay, so you should have found that the f inverse of x was equal to 3 divided by the quantity of x plus 1. And you found that by step 1, let f of x become y. Step 2, switch the x and the y. Step 3, resolve for y, and that gives you f inverse of x. Now, a point that I forgot to make on that last one here. What is the domain of my inverse function here? All x such that x is not equal to what? Looking at this function, x, it cannot be 3, right? And what's the range of this function? All y such that y cannot be... Well, let's go back and look at the picture. What's the one thing that y can't be? Check it out. It's right there. So it's 0, right? So not 0. And what do you notice about this box right there and this box over here? They are what? They are opposites of each other. So the domain of your regular function becomes the range of your inverse function, and the range of your regular function becomes the domain of your inverse function. So I wanted to point that out to you. Okay? And then the last idea that we're going to talk about today is how do we verify f inverse of x? How do we verify that it's correct? Okay? Well, in order to algebraically verify that f inverse is correct, you have to do 2 things. The first thing you have to do is you need to show that f of f inverse of x is actually equal to the identity x. And the second thing you got to show is that f inverse of f of x is equal to the identity x. So it's interesting that it equals the identity because that's exactly the line that they are reflected upon when you graph these, the line y equals x. So what we're going to do is we're going to actually verify that these two functions are correct. So we started with f of x was, what was it, 5 over x and then plus 3. Is that right? Yeah? Okay, and then we found that f inverse of x was, what was f inverse of x?
X plus, or 3 over 5 over x plus 3.
5 over x plus, no, that's not right. Is there a minus sign? There you go, 5 over x minus 3. There we go. Okay, so we need to show that f of f inverse of x gives us back x. So we need to actually physically, algebraically show that f of f inverse of x, which is 5 over x minus 3, is actually equal to x. So that means that I am going to replace this right here with a 5 over x minus 3. This is function composition. This is what we did last section. So that means I'm literally going to have 5 divided by the quantity 5 over x minus 3, and then a plus 3 on the outside. So does everybody see how I have replaced or have evaluated f of f inverse of x? Yeah, it's kind of hard to see. Do you guys get it, though? Okay. So now all I have to do is verify that this does indeed equal x. So check this out. This is like 5 over 1 times x minus 3 over 5. And I want to verify that this equals x. Well, yeah, check it out. The 5's cancel out, and all I'm left with is, oh, I forgot the plus 3. X minus 3 plus 3. Does that equal x? Yep, it sure does because the 3's cancel out. X equals x. That one checks out.
Wait, did you say, like, the functions have to pass both of these tests?
Yes, it has to pass both. Yep. So I just showed that f of f inverse of x does equal x. Now I got to show that f inverse of x also equals x. So we'll do that one too. So I literally want f inverse of f of x was 5 over x and then plus a 3. And I want to make sure that this is equal to x. So I'm going to take everything that I see here, and I'm going to plug it into the inverse function, which is right there, for that x. So I end up with this. I end up with 5 divided by, now I'm replacing x with a 5 over x plus 3. And then notice I have a minus 3 in the denominator. Well, some really nice things begin to happen. I get 5 over 1, all divided by 3 minus 3 goes away. This is like 5 over x. When I take 5 over 1 and I multiply by x over 5, the 5's cancel. Check it out. I get x and is equal to x. These are the identity. And it's the exact same thing as, or it's not the exact same thing, but it reflects the line y equals x in the actual problem there. So I bring those back. You got to show that these equal the identity. 5. Okay, so as an example, last one for the day, we're trying to see, prove that these two functions are inverses of each other. Okay, so we're going to check this. We're going to check f of g of x, and we want to get back x, and we're going to check g of f of x, and we want to get back x when we check these things. So this is going to be f of g of x is the cube root of x minus 5. So that means that I'm going to plug all of this into my x function. So I'm going to get the cube root of x minus 5. And I'm going to cube all of that, and then I'm going to add 5. So everybody see that the highlighted parts all fit into each other? Okay, good. And then do you notice what's happening here? Check it out. The cube root of something cubed gives me back x minus 5 plus 5. So x minus 5 plus 5. Hey, check it out. I get back an x. That's good news. All right, and then on the other side, if I check g of f of x, I really want a g of the f of x function, which is x cubed plus 5. So I'm going to replace everything I see here right there into my g function. So that's going to give me the cubed root of x cubed plus 5, and then I have a minus 5. Well, that's just the cube root of x cubed because the 5's cancel out. Cube root with something cubed, hey, check it out. That equals x, and that is the identity function.